Now, today we'll go into Hooke's law, stress strain, and the Young's modulus. Okay, so the next part after the work, energy, and power. We'll revisit a little bit about Hooke's law, and then we will enter the new stuff, which is stress strain and the Young modulus in your physics AS level. Okay, so let's start with Hooke's law. Now, for Hooke's law, study is about elasticity, right? What is elasticity? I take a spring, compress it, and it returns to the original position, original condition. I take a rubber band, I stretch it. When the force is removed, it snaps back. Again, it returns to the original position. Now, what if I take a plasticine and I compress the plasticine? Will it return? It will not return to its original position, right? It will stay compressed. You see, all of these objects, they have a property. What is the property here? The property here, we are talking about the ability of the object return to its original state. That property of the material, we term it as elasticity. Okay, now what makes an object elastic and what makes an object inelastic? It is the behavior of the molecular structures of the substance or of the material. You see, when I apply tension, tension means stretching. Okay, I stretch it apart. I apply tension. What happened to the molecular structure of the substance? These are the atoms. I stretch it apart, so I am applying a force, trying to pull them apart. So all the spacing of the molecules increases. Okay, they become further from each other. Now, after I remove, they come back. Okay, same thing. I try to compress. After I remove the force, they come back. So always, elastic material, when force is applied, they are always trying to resist you, because based on the spacing, okay, they will maintain whichever spacing that is best for them. If you try to disturb the spacing of the molecules, in the sense that you try to increase or decrease it, then they will always return. They want to come back to the original state. They don't like being disturbed. Okay, so this intention of the particle trying to come back is what gives rise to the force, and we call the force a restoring force, because they are always trying to restore, right? They restore. You stretch it, they restore. You compress, they restore. That's why we call it restoring force. And this restoring force is the force developed in the elastic materials. Okay, is it found in elastic material? Yes, but not as big, okay, as compared to the elastic materials. Okay, so elasticity of a material comes from the nature to which the material is designed. Okay, innately it has by nature. Okay, the arrangement of the particles, okay, is what gives the elasticity. Now, take an example of okay, when you think of elasticity, the best example is just springs, all right? Springs, so Hooke's law, we learned all that in the previous lessons, all that. Right, so take an example of a spring. Okay, if you put a spring without putting a load, so this length is the original length, right? Now, the moment I attach a load on it, it got stretched. Okay, the moment I put the load on it, then a force is applied to pull the string down. What happened is that the last particle in the spring, he got stretched away from the particle next to it. Again, you try to disturb the spacing, then it tries to resist. It tries to come back. So that trying is that is what gives rise to the restoring force. So immediately when you stretch it, the restoring force is developed here. So force upward and your load is mg downward, but this force is very, very small. At first it's very, very small. So as you try to pull it down further, the extension measured from the center to this dotted line, okay, the starting position, X, sometimes they will give E, okay, X or E. The extension, as it gets bigger and bigger, then the force will increase and increase and increase. Eventually, at one point, it is going to be the same as the mg, and that is when equilibrium is achieved. Okay, this force, what type of force is this? This force is a variable force. Is it a constant force? It is not a constant force because it changes according to distance, right? The greater the distance, the greater the force. So it is never a constant force. It is a variable force. Now, according to Hooke's law, what does Hooke's law say? Hooke's law says that the force is directly proportional to the extension, right? So as you go further and further down, the force increases. Okay, so imagine like you pull this load, you apply extra force, you pull it down. Okay, you notice that the further you go, the harder you pull it, right? You have to exert more force to pull it. Okay, so the force that you exert is the same in terms of magnitude as the restoring force. They are different, but they are same in terms of magnitude. How do we measure the restoring force? Because we can't actually go inside the spring and measure it, right? So what we can do is we measure the load, and we know that the load is having the same magnitude as the restoring force. Okay, so meaning that this force can be the restoring force, or I can say it is the applied force. They are the same in terms of the magnitude. So force is directly proportional to extension. If I want to make this into equations, I just add a constant here, F equals to Kx. Okay, now F, restoring force and applied force. Okay, we talked about that one. And K is called the spring constant, right? The spring constant, or we can also say it is the force constant, another term. Okay, it's actually the same thing. A force constant. What is the spring constant? Okay, technical definition, you can say, okay, spring constant is force divided by distance, extension, right? So it's the force needed to stretch one unit length. If you just think of it, common sense, high spring constant, what does it mean? It means that you need more force to pull it by 1 cm. Okay, low spring constant, then you need less force to pull it by 1 cm. Okay, it can be pulled or it can be compressed. So that is spring constant. Now, that is technical definition, right? But what does it really mean, spring constant? Spring constant, we say that it is actually equivalent to stiffness of the material. What is meant by stiffness? Stiffness is like the ability of the object or the material resist the change in the length. Okay, resist the change in the length, can be decreasing length or increasing length. That is stiffness. Now, don't confuse stiffness with strength. What's the difference between strength and stiffness? Stiffness measures the resistance. Okay, how hard it is trying to resist you. Strength is a measure of how much force total to break it. That is strength. Okay, again, stiffness is the resistance, right? This is the resistance. Resistance to change in length. Okay, we can say that, to change in length. Now, strength is the total force total F required to break it. Two different things. Okay, but generally they are kind of related, but not directly related. So usually high stiffness will have high strength, but not necessarily, not all the time. Okay, so that is the difference between stiffness and strength. Okay, so here we are talking about the spring stiffness, the spring constant. Okay, the graph, since this is a variable force, so we have force against distance. If you plot the graph, you get a straight line because it's directly proportional. Until where? Is it forever? No. Until a point, this point, beyond this point, it starts to curve like this. Okay, so it starts to curve beyond this point. What do we call this point? Is it elastic limit? No, it's not elastic limit yet. Okay, this point is, we call the proportionality limit. Proportionality limit. Okay, beyond this point, beyond this limit, is no longer proportional. Meaning that after this point, this graph will start to curve. It only remains straight line until here. Okay, so where is the elastic limit then? The elastic limit is slightly further than the proportionality limit. This is the elastic limit, somewhere here. I'll name it E. Okay, so this is X here. So once the spring reaches the proportionality limit, what happens? Will it return? Yes, it will return, okay, because it's still inside the elastic limit, right? But what happened is that the extension is no longer predictable. If it was a straight line, you can predict, right? Because the gradient is the same, you can predict. If it's a curved line, then the gradient is changing every unit length. So you cannot predict the extension. You can see from the graph, the shape of the graph. Here, initially, it's like straight line and then curve like that, right? So if you take 1 unit length, let's say this is 1 unit length, 1 unit, and this is 1 unit. How much is the change here? From here, this is the amount of change in force. For the next 1 unit, from here, this is the amount of the change in the force. The change is less, okay? It decreases, no longer the same. So when the graph starts to curve, then the extension becomes unpredictable, and you realize that you actually can feel it. When you imagine like you stretch a string, you stretch it all the way until it breaks. At some point, you feel like suddenly it becomes very easy to stretch. At that, only that particular instance, you feel like the structure of the molecule like wears out. Okay, it weakens. Okay, suddenly you have like you stretch very hard, right? Suddenly, boop. Okay, suddenly very easy, you can stretch it. Okay, only happen at that point. That is when the elastic limit or the proportionality limit has reached for the spring. Okay, you continue to stretch it. If you stretch within the elastic limit, you let go, it returns, it snaps back. If you stretch beyond the elastic limit, what happens? It stays there. Okay, because energy is lost. Later we'll come to the energy. Okay, we'll save it for later. So if you stretch beyond the elastic limit, then it will not return to the original state anymore. Okay, so it's exceed. We say that it exceeds the elastic limit. So Hooke's law only apply where? Within the elastic limit and within the proportional graph over here. So when you calculate energy work done, right, is equals to the area under the graph. So work done equals to force distance, area under the graph equals to half force distance, because we are dealing with this triangle here. Okay, so area under the graph is equals to EPE. So I can write EPE equals to half kx squared, since F equals to kx. Okay, so here is, I calculate the elastic potential energy. And which part I'm calculating? Up until the proportionality limit over here. Okay, so that is for, yeah, another term for the EPE, elastic potential energy. Sometimes you see this word strain energy. Okay, strain energy is the same as elastic potential energy, same thing. Okay, just different term. Okay, next one, we will look at one example of a combined spring system. Okay, now let me go to the next page. If you want to take a screenshot, you can take now. I'm going to go to the next page. Okay, example 1. Which combination of springs will give the greatest extension? Okay, now before we do the calculation, just try to think of it like qualitatively, without calculation. Which one you think is the maximum greatest extension? Is it the series one or is it the parallel one? The series one is like the first two, from tip to tip. Okay, tip to tip. Okay, I haven't said parallel, the greatest extension. Okay, let's see. Now, the parallel is side by side, right? Side by side. Okay, you can imagine the parallel is like the gym equipment. If you go to gym, like you train back muscles. You see, like got the two handle, and then in between there are many strings. You pull it, you train your back muscle. That one, right? So that is like for an example of the parallel spring systems. Okay, so parallel, the answer is parallel spring system will have a lower or smaller extension compared to the series. Okay, why? Because you see the force is being shared by the two springs. You have 6 Newton pulling down here. 2 springs are pulling at the same time, at the same height, at the same length. So the force got divided between these two. So maybe 3 Newton here, 3 Newton here. It's not the same with the series. If the series, 2N pulling down, same here. This is also 2 Newton pulling down. Okay, because you are just joining the string one after another. They are not doing the work together, right? Just one after another. So it's the same thing. When you apply 2 Newton force, it's the same for every strings, for every spring. Okay, now let's find out which one is the greatest extension. Okay, let's start. How do we solve this? Now, first, you can do it like this. First, we will find out. Imagine this is like only one spring, 6 Newton. What would be the extension X? We can use F equals to Kx. Before we solve this, imagine just one spring, okay? Just one spring and then acted by the same load. What would be the extension? Okay, we can find it easily. X would be equals to force over K. And the force is 6 Newton, right? So X equals to 6 Newton over K. This is the extension if it was only one spring, correct? If it was only one, this is the extension. Now there's there's 2, 1, 2. So if there's 2, then this extension will be shared by the 2 spring. Okay, so looking at the system, 2 springs, then I would take the extension 6 over K. Since they got shared by 2, right? Then I just divide by 2. Okay, I take the extension, divide by 2. Equals to, okay, equals to 3 over K. What is this X? This is total extension of the spring system. Okay, because the force got shared, the extension got shared. Okay, so here I box this. Total extension of this number 3 is 3 over K. Okay, assuming all the springs, they are all identical, so they have the same spring constants. Let's look at the next one. The one on the right, 3 springs suspending 8 Newton load. Okay, again, we try to find, what if it was only one spring? What is the extension of one spring? Okay, then we do F equals to Kx, X equals to F over K, and that's 8 over K, X. What is this extension? This is the extension if there was only one spring, and if I put 3 springs, then they share the extension. So I take this extension, divide by 3, right? I divide by 3, then I get the total extension equals to 8 over 3K. Okay, so here it only extends this much X total. Okay, each and every springs, they share the same extension. Okay, so we have 3 over K and 8 over K. How about the first two? Let's solve for the first two. Now, for this one, same thing. I do the same thing. What is the extension if there was only one spring? 2 Newton. Okay, F equals to Kx, X equals to F over K. That's 2 over K. That is the extension of one spring. So if I connect another spring after this one, I connect below. Okay, does it affect the extension? No, it doesn't affect the extension because the same force are pulling each strings. So meaning that whatever the extension here, X equals to 2 over K of one spring, this, you add one spring, the extension would be the same. X equals to 2 over K. So you are adding the extension. You are not dividing. You are adding the extension for the series arrangement. Okay, so meaning that the total extension would be 2 over K plus 2 over K equals to 4 over K. X total. Okay, now how about the second one? If you look at it like this, it's very hard to tell because this one got 2 springs, 2 Newton, and this one got 3. Should be longer extension, but the weight is 1 Newton. So it's very hard to tell sometimes. So you have to use the calculations. Okay, so we prove it, calculate quantitatively. Same thing I do. Imagine it was acted by only one spring, 1 Newton. What is the extension? F equals to Kx, X equals to 1 over K. This is the extension produced by one spring if it's hang by only 1 Newton. So since you have 3 springs and the force is acting the same on each and every spring, 1 Newton, 1 Newton, 1 Newton, then you have 3 times of the extension. 1 over K, 1 over K, 1 over K. So you have 3 over K. X total equals to 3 over K. Okay, now, which one is the greatest extension? You have an unknown here, K. You just sub any value for K, then you can see clearly. If K equals to 1, then this is 4, this is 3, this is 3, this is 8 over 3. So the greatest extension would be the first one. A. This system gives you the biggest extension. Okay. Now, again, for parallel, what happened to the extension? It got shared among the strings. So if there are 3 springs, I divide by 3. If there are 2 springs, I divide by 2. For series, whatever the extension here, plus the extension here, plus the extension here, that is the total extension. Same with this one, whatever the extension here, plus the extension, I get the total extension. What do we understand about the force? The force is being shared for the parallel system. So 8 Newton is being divided by 3 here. In the parallel system, force is shared. Force shared. In the series system, force is same. Okay, so force in series are the same, and in parallel, they share. Okay, let's go to the next one. Example 2. When an object of weight 15 Newton is hung at the end of a spring, the extension is 4 cm. How much is the extension of the weight? Is 25. Okay, we can just do K equals to F over X equals to 15 divided by 4 cm equals to 3.75 Newton slash cm. Okay, so how much is the extension if the weight is 25? So we do F equals to Kx. Okay, so first you get the spring constant. This is given to you to find the spring constant, and then you use the spring constant to find the extension if the weight is 25. Okay, so we have 25 equals to 3.75 x. Okay, so x equals to 3.75. That's equals to 6.67 cm. Okay, so extension is 6.6 cm. If I take this spring with 25 Newton load, right? Okay, then B. The same springs are connected as shown below. What is the extension in each case? So we use the same spring and we do this connection. What is the total extension? Okay, remember our method. First, what do? We find the extension for one spring that holds 30 Newton. Okay, we have a force of 30 Newton here. First, we get the extension for one spring that holds 30 Newton. So it's like this. We have a 30 Newton. Okay, now F equals Kx, so X equals to F over K. 30 Newton divided by the spring constant, 3.75 equals to about 8 cm. Now, once you get the extension of one spring That is very easy. You just apply what is the rule of thumb. In each level, here I would say level 1, level 2. There are 3 springs in the first level, meaning that the extension 8 cm will be shared by the 3 springs. Remember, parallel, extension, shared, right? So in this level, 8 divided by 3. 8 cm divided by 3. That is the extension for the first level. Now, for the second level, you can see second level, level 2, this one is in series with level 1, right? It is under it. So series, the extension is, here is 8 cm, right? If it's series, sorry, let me draw it here. If you have a spring like this one, right? If you draw series, if this has an extension of 8 cm, this should be having 8 cm as well. So each level has the same extension. The first level, 8 cm, is divided by 3. The second level, 8 cm, is divided by 2 because 2 springs are sharing it. Okay, so we take 8 cm divided by 2. That is the total extension. Okay, so 8 divided by 3, that's about 2 point, let me write it here. It's about 2.67 cm. And 8 divided by 2, that is 4 cm. So level 1, 2.67, level 2 is 4. Total extension would be 2.67 plus the 4, 6.67 cm for this system. Okay. Okay, the second one. This one more complicated, right? How many levels we have? 1, 2, 3, 4, 5. Okay, we have 5 levels and different springs. Okay, it's the same thing. Now, what is the first step? Find how much extension if it was only 1 spring. 1 spring attached to 40 Newton. X equals to F over K. 40 divided by the K, 3.75. Okay, so extension is 10.67 cm. Each level having 10.67. Then you only have to see how many springs. The first level, 1, 2, 3, 4. They share the 10.67. So 10.67 divide 4 equals 2.67. Okay. Second level, another 10.67 divide 3 springs. So 10.67 divide 3. 3.54 cm. Third level, 2 springs. 10.67 divided by 2 equals to 5.34. This one only 1. So just take full extension, 10.67. The last one, 2 springs, divide 10.67 divided by 2. Okay, same as 5.34. What is the total extension? This one plus this one plus this one plus this one plus this one, which gives X total of the system. It is 27.56 centimeter. Okay, you can approach it to 77.6, same thing. Okay, so that is on finding the extension of multiple spring system. And sometimes the question will also ask, okay, what is the effective spring constant? What does it mean by effective spring constant? Okay, let me go to the blackboard. Just a second. Okay, erase this one. Okay, now in general, we can say, let's say we have two parallel spring, K1, K2, attached to a same weight. Force here, F. This is F1, this is F2. We know that force equals to F1 plus F2, right? Okay, because the force are shared, right? Shared in the parallel springs. Okay, then we put in F1. What's F1? F1 is equals to K1X. Okay, you can say K1X1 plus K2X2. But the X are the same because these two springs, they share the same extension. So I can just write it as K1X plus K2X. Okay, same extension. Now the F, this F is the total F, correct? So total F, if I take the Kx, that is K total X total, correct? Okay, I'm just substituting the F equals to Kx. So K total, X total, but the X total is the same as all these X's. Just cut off this. I have K total equals to K1 plus K2. K total means K effective. So the effective spring constant is equals to K1 plus K2. Effective, like combined, the combined effect of this system. Okay, so if you want to calculate the extension, you can also take force equals to, this is the total force, F total equals to the effective spring constant. And that extension would be the total extension. Okay, so this is to get to the relationship between the spring constant. This is what you want to remember. This formula here, okay? So the total spring constant is equals to K1 plus K2. If you have another string, then you plus K3 plus K4, K5 plus and so on and so forth. If it's not the same, the K is not the same thing, we just add it. We just add it up. So for parallel, if they ask you to find the effective spring constant, just add it up. Okay, add it up. How about for series? Okay, one spring, another one. Force here. What we understand about series, force is the same. So F1, this is F2, okay, just F1, right? F2, okay, I can just say F2 here. F2 is the same as F. Okay, the force are the same. Now, what we know about the series, other than the forces, we know that the extension total, right? If this is X, if this has an extension of X, if this has an extension of X, X1, X2, then total, I just add it up. Remember our level 1, level 2, level 3, we add it up, right? So total extension would be equals to X1 plus X2. Okay, from here, again, X1 is F1 over K1, right? So F equals to Kx, right? So X equals to F over K. F1 plus K, sorry, F1 over K1 plus F2 over K2. But these two are the same, so I can just put F K1 plus F K2. Okay, yeah? Now then the X total, this X total is equals to the force total. The force total is the same as this force, right? So I don't have to write anything, just same F, because all this F is the same. Force total over effective spring constant. Okay, because this is the total one. This is total one, the entire system one. This is for the individual spring. Individual spring. Okay, now from here, discard all the force. So I have 1 over K effective equals to 1 over K1 plus 1 over K2. And here I arrive at this equations. And again, you need to remember this. This is applied for series arrangement. The effective spring constant is the reciprocal summation of individual springs. Okay. Okay, so now it's 47. Okay, usually I give rest after 1 hour, but never mind, we'll do it earlier. I give you 3-minute rest and we come back, we continue to the next part, the stress strain and Young modulus. Okay, so 7:50, we come back. Okay, 7:50, 51. If you want to drink water, go toilet, okay, do it now. Right. Okay, we are back. Okay, now let's continue, guys. So now we will enter the stress strain and Young modulus. Now we have recapped the spring constant. So it is a measurement of the stiffness, right? Stiffness of a spring. Let's say I have two springs made of the same material. So one is thinner and one is thicker, a larger cross-sectional area. Same material, but dimension is different. One is thinner, one is thicker. The spring constant will be different as well, right? Because the spring constant, sometimes it depends on not only the material, it depends on the size, the thickness, all right? And how many wires, how many coil of springs in between, all that. Okay, spring constant depends on all this. There are many factors that can change the spring constant. So the dimension is the first one. It's one of the factors that can change the spring constant. Now, my point is, they are the same material, but one is thicker. This will have a higher stiffness or the higher spring constant. This will have a lower spring constant. Okay, so the spring constant depends on size and dimension. Even though it is the same material, different dimension, spring constant, different. Now, in the industry, in the engineering industry, the stiffness is very important. It's a very important characteristics. If you're talking about, let's say you're talking about like constructions, buildings, constructions of buildings, you use concrete, right? Concrete, and then they mix with what? They mix with steel bar. Why do you want to mix with steel bar? Because steel bar or steel has a high stiffness. Okay, they have a high resistance to forces, so they can withstand pressures. If you have pressure, tension pulling it, you have compression force, or you have twisting force, whatever forces coming, the resistance of the steel bar is very high. It has a very high stiffness. That is why they usually combine, they mix, okay, concrete, the cement, okay, with steel bar to increase the effective stiffness of the structure. Okay, that is for construction. So stiffness is a very important characteristics. In the aviation, the design of airplanes, okay, most of the parts of the airplanes are made of composites, okay, carbon fiber composites. Okay, why composites? Composites is because of lightweight. We want airplane to be strong, resistant to forces, and at the same time lightweight. Okay, so again, the stiffness is also very important because stiffness of composite is very high. Okay, the good thing about composite, okay, the material that will be used to make aircraft, is they have high stiffness. At the same time, they have a low density. They are very light. Okay, they are very lightweight. Okay, because when you're flying in the air, there are it is subjected to a lot of forces coming everywhere, right? The turbulence of the wind, okay, the pressure differential, a lot of forces. So you need to have a high stiffness. Now, the bottom line, the point is, stiffness is a very important in the industry. But in the industry, we do not use spring constant. We have another stiffness measurement that we call the Young's modulus. What is the difference? Young modulus is also measure of stiffness. Okay, it is the same, almost the same as spring constant, measurement of stiffness. But Young modulus is the stiffness to a specific material, to a what? To a specific material, and it does not depend on size and dimension. For example, you take copper. If you have copper, cross-sectional area, small or big, they have the same Young modulus, the same stiffness. Okay, it does not depend on the size and the dimension, unlike spring constant. Okay, so take note. This is the difference between these two. Okay, let me write this down for you. Okay, so spring constant is the characteristics of specific sample of a material. Okay, and for Young's modulus, Young modulus is what? Is the characteristic the same? Is the characteristics of a material type. Okay, they are both the measure of stiffness of a. One is to a specific material, so it's specific to spring only. Another one is specific to a material type. So if I talk about steel, then steel has the Young modulus, regardless of the dimension. They have one Young modulus. Okay, now Young modulus of steel. Okay, here are a few examples of the values for steel, plastic, the common ones, plastic, rubber. Usually, Young modulus is very huge. The value is very huge. It has a unit same as pressure. So steel is about 210 gigapascal. Okay, later we'll come to what is actually Young's modulus, just to give you an idea here. Okay, it is a measure of what? Stiffness. So meaning that the higher it is, the stiffer is the material. Not spring, is material. The stiffer is the material. Okay, so stiff material means that they can resist tension, compression. They are very good at resisting all this. Okay, so steel is 210 roughly, and then plastic is about 2 gigapascal, and maybe rubber is about 0.02 gigapascal. Okay, now when you apply stress or when you apply force on a material, then we say that the material will deform. Deform means change of shape. Okay, change in shape or change in length. That is the meaning of deform. DE, deform. Okay, deformation of solid. So whenever stress is applied, whenever force is applied on a material, then the material will be deformed. Okay, how many types of deformation are there? You can see here. Okay, compression, the first one. Compression is like you compress the both ends, you like squash it. Okay, you compress it. Compression. So this is the first deformation. The second one, we have tension. Tension is like you have a rod or you have a bar, steel bar, you pull the edges, you stretch it, okay? That is tension. And we have bending. What's bending? Bending, you apply, you pull the side, okay? It's like this pen. I pull the side down and then I push the middle up. That is bending. Okay, bending. So that is the third type of deformation. And then what we have? Torsion. Twist. Okay, twisting. That is torsion. And the last one is shear. Shear is like the force is applied along the cross-sectional plane. You see, what does it mean? This is the cross-section, this plane here. Imagine like if I cut it in half, then you see this plane, right? So the force is applying, like the force is parallel to the plane. This one go here, this one go here. Opposite direction, parallel to the plane. So it's like push it like this. That is shear force, okay? So there are many forces that can deform a material. There are many types of deformation, okay? But we only focus on two in our syllabus, okay? We only focus on the first two, compression and tension. This compression and tension is we only need to deal with one dimension. It is only one dimension. The two forces is in one line. Okay, same with the tension, pull and push, they are one-dimensional forces. Shear, bending, all that they are two-dimensional. So we only look at compression and tension. Okay, now, so force applied causes, okay, there are two types of forces, right? So here our focus is tension and compression. Whenever force is applied, object will deform. And there are two types of deformation. First is elastic. Second one is plastic. Elastic deformation and plastic deformation. Okay, what does it mean by elastic? Elastic deformation is when the object deforms, okay, when it changes the shape, it is able to return when the force is removed. Just like spring, okay? You release, it snaps back. That is elastic deformation. The moment I stretch it, it is deforming. So there are some changes in the structure, deforming. But as long as it is in the elastic limit, it is able to return. That behavior we say elastic deformation. Okay, so if you look at the structure of the molecules like this, these are the molecules. I'm stretching it apart like this. These are the force applied. Okay, I'm stretching it apart, and again the molecule tried to resist by pulling me, right? This is like the intermolecular forces of the molecules. The moment I stretch it, it resists all that. So whenever the force applied is being removed, okay, all this I removed, then it will return because of this, the bonding, the intermolecular forces bonding. So that is elastic deformation. Okay, now for elastic deformation, what happened to the energy? Energy is stored. Okay, energy is retained, we say, retained. You do work on the spring or a copper steel, whatever, you do work on it, you apply tensile stress, you apply tension, then you're doing work, meaning that the energy is stored in the spring, right? The moment you released it, then now comes the spring doing the work. Okay, the moment you release, the spring do the work by restoring, retract. Okay, so that is also from the energy that given to the spring. So the energy is retained, right? You stretch it, energy is retained in an elastic deformation. Okay, let's look at plastic. Plastic deformation is when you stretch beyond the elastic limit and the object does not return back. Okay, the material does not return back. So what is happening in plastic deformation? If you look at the molecular structure, let's say this is this, let's have a close-up look at the molecular structures. Imagine like this is a copper rod. Okay, I stretch both ends of the copper rod. The molecular structure like this. What is happening in plastic deformation? The particles, the structure, they are sliding over the plane. If I draw one line, this is the plane of the structure. this whole thing slides to the right, and this whole thing slides to the left. So it's like they are sliding over one another. It's not the same as elastic. Elastic is like the two particles here, I pull it, and then they come together like this. So the force is parallel to the bonding. It's parallel to the intermolecular forces here. So they return. The bond is able to withstand the force. But this one is more like due to the structure, not the bonding. It's due to the structure, how it is arranged. The moment I stretch it, then this particle, this line, slides over one another. So it deforms, okay? Of course, it's deformed, the shape changes, and they can never come back because the structure has already changed. You cannot come back. If you stretch the bonding can pull it back. But if you stretch the structure, then it cannot come back. That is why it remains permanent. We say permanently deformed. Okay, so this is plastic deformation. Plastic deformation or permanent deformation. Okay, due to a change in the structure itself. Due to the change in the structure itself. Okay. Now, what happened to the energy in plastic deformation? Is the energy stored or lost? If you stretch a spring within the elastic limit, the energy is always retained, yes. The moment you stretch beyond the elastic limit, then a lot of the energy will turn into heat energy. Okay, that is why when you release, it cannot return because it has no more energy left. All the energy has turned into heat. The moment you stretch to the plastic deformation, then the heat is produced in the structure. More energy is lost to heat and the object cannot return. No more energy stored in the material. So the material cannot do work. It remains plastically deformed, does not return to original position. Okay, so here we say energy lost into thermal. Okay, one example of this is like the cheap spoons. Okay, you may have used the cheap spoons. It's like easily they bend, right? Easily they bend. So that is plastic. Okay, you bend it, you retain this shape like that. Okay, it does not return. That is example of plastic deformation. A plasticine, okay, is a plastic deformation. Plasticine is a little bit different because the nature of plasticine is flexible, right? So it's a little bit different. So that is the difference between plastic and elastic deformation. Now we move on to the next one, which is the stress and the strain. Okay, let me erase this. Okay. Stress strains. Let's look at stress first. What is stress? Why do you feel stress? Because of pressure, right? Exam, pressures, homework, pressures, or whatever reason, no reason at all, you feel stress. Okay, so whatever is the reason, stress is due to pressure. So in physics, in here, the study of materials, stress is same thing, pressure. Okay, so stress is pressure, so means that it is force per unit cross-sectional area. Okay, same definition with pressure, right? Force per unit area. But here, we added cross-sectional area. When you define stress, guys, you have to mention cross-sectional area. Remember, If you just write area, they give you wrong. You have to mention cross-sectional area. So force per unit cross-sectional area. So let's say you have like a steel rod. This. Okay. I apply tension. Tension is what? Stretching, right? Stretching. So tension. Force here, force here. Now, when I apply tension, stretch it, this area, cross-sectional area, meaning that this area over here, area, if you take the tensile force divided by the area, then you get the stress applied on the material. Okay, so the unit is same as pressure. Pascal, how about the symbol of stress? The symbol is sigma. Okay, sigma equals to force divided by area. So force is in Newton meter square. Same thing, this is Newton / meter square or Pascal. Okay, so stress equals to force per unit cross-sectional area acting on the material. Okay, now because of stress, the object experience strain. Okay, strain, what is it? Strain is the change in length per unit original length. Because of this stress, this pulling, the material experiences a elongation, an extension. So up to here, let's say this much change in length. Okay, or I can say it X, or sometimes you'll see E. They're all the same thing, extension. Okay, so the original length of the object, L, plus the extension, okay, after you apply the force. Okay. Now, for strain, strain is the change in length per unit original length, meaning that it is X over L. The change in length, that means the extension, X, per unit original length, so divided by the original length L. This gives you the strain of the material. Now, it has a symbol of this epsilon. Okay, epsilon equals to X over L. Okay, so again, you apply stress. The stress can be in the form of tensile or compression, pulling or pushing. Okay, the stress. If you take the force, you divide by the area of cross-section, you get the stress. Okay, now, and then under stress, when the material is under stress, it will experience a strain. That is the extension. So that extension, that strain is calculated by the extension divided by the original length. Okay, now this strain, right? Let's say if I say the strain is 2, what does it mean? Because this, the unit of the extension is meter, the unit of the original length is also meter, so they cancel out, no unit, meaning that this is actually a ratio. Okay, a ratio of the extension to the original length. So if I say the strain is 2, what does it mean? Meaning that for every unit length, the extension is 2, twice of it. Okay, 2 meter, 2 centimeter for every unit length. Okay, now, and sometimes you see the strain will be given in percentage. It will be given in percentage because it's just ratio, right? You can change it to percentage. So, example, they say 200% of strain. What does it mean? 200% would be same as this one. Strain is equals to 2 to 1. Okay, because we have our formula, strain in percent is you take the X over L, you just times 100, you get a percent. Okay, so if it's 200%, that is the same as 2. Okay, just sometimes that you'll see it is expressed in percentage. Okay, sometimes it's percentage, sometimes it's in ratio. Okay, so we know that now. We know that what is stress and what is strain. Now we come to the Young's modulus. Okay, what is Young's modulus? Young's modulus is a ratio of stress to strain. It is given by a symbol capital E. Okay, the Young modulus of a material is the ratio of the stress to the strain. So I'll write here ratio of stress over strain. Okay, what does it mean then? It represents what? What does it represent? It represents, I said earlier, what is it? It represents stiffness, right? Stiffness of a material. And also, it does not depend on size of the material and also the dimension of the material. So it becomes a more common measurement in the engineering industry because the size does not affect. Okay, not like the spring constant. So Young's modulus is represent the stiffness of a material. So what is stiffness again? Resistance to force. Okay, stiffness is just how much extension under force. How much extension under force. It is not the same as strength. Stiffness and strength. You often see these two words, stiffness, strength, but they are not the same. What is strength? What is strength again? Strength is the amount of force needed to break that material. Stiffness is the resistance. Okay, so that is the Young's modulus. So the higher the Young's modulus, the stiffer is the material. Because you see, if Young's modulus is high, that means you have a high stress, low strain, correct? So high stress, low strain, meaning that large stress is used to produce small strain. So it means that it is stiffer. Okay. So just to give you a little bit of idea of different materials, like the one mentioned earlier, the steel. What is the stress? What is the Young's modulus of steel? All steel. Okay, of course you have many types of steel. You have mild steel, okay, strong steel, many types. So we're just talking about steel in general. The Young's modulus of steel, it's about 2 times 10 power of 11 Pascal. Now, don't be surprised with the values. The values are usually that big, yes. So when during the calculations, right, if you calculate what's so big, the value is normal, okay? So the Young's modulus value is very big. So it's 2 times 10 to the power 11 Pascal. If you come down to rubber, you see the difference is already this very big difference. Steel, I come down to rubber. Okay, so rubber is still very high. It's about 2 times 10 power of 7 Pascal. Okay, why the unit is Pascal? Because the stress is Pascal, right? E equals to stress over strain. This is Pascal. The strain has no unit. So your unit for Young modulus is Pascal. Okay, 2 times 10 and this one. Okay, now the graph, you see, E equals to stress over strain. I can write stress equals to E times strain. y equals to mx plus c. If I plot a graph of y against x, or the stress against strain, you have a graph sigma against epsilon. What do you get? You get a straight line. Starts from 0, like this. Okay, what is the gradient? The gradient is the Young's modulus. You see, this is very, very similar to your spring constant. Your spring constant is force against extension, correct? And it's a straight line as well. What is the gradient here? The gradient here is the spring constant. But in a stress strain graph, the gradient is the Young's modulus. Okay, this is for spring. This is more universal for material. Okay, how do you identify which one has a larger Young modulus? Which one is stiffer? If I have material 1, material 2, which one is stiffer? The one with the higher gradient. Material 2 is stiffer because it has higher gradient. Okay, now E equals to stress over strain. So if you know the stress, you know the strain, you can calculate E, right? Now I can also express this in stress is force over area divided by, this is x over original length, equals force over area times L over x. So FL over AX. This is Young's modulus formula. Please remember this. You know the force, compression or tensile, okay? Torsion, all those won't be asked, okay? Just compression or tensile. You know the force, you know the area. What is the area here? Cross-section, okay? Cross-sectional area. And the length, original length, plus the extension, you can get the Young's modulus of the material. Okay, how do they determine the Young's modulus? They do it experimentally, right? They use the what? You may have seen this, the hydraulic press, right? You just, like, people just throw in random stuff and they use the hydraulic press, right? So the same thing, they use that, but it's like they use it to pull. Okay, they use the hydraulics to apply tension on a material, and usually the material, they make it like this. They make it like a rod, something like this, and also, or they make it like a dog, like a bone shape, dog bone shape, like this, and then they pull both ends like this. They calculate everything. They calculate the force, they calculate the stress, the strain, and then they use the calculation to get the Young's modulus. Okay, so Young's modulus is determined experimentally. Okay, experimentally. Okay, examples. Go to the next slide. Okay, example 1. A wire has a final length of 6 meters after undergoing a strain of 200%. Now, you see, it's given in percent. What is the original length of the wire? Okay, strain 200%. What is the strain formula? We can write strain equals to x over L. This is original length, huh? Okay. So strain 200%, meaning that this is in percent, so I times 100, right? So this strength is in percent. So I bring the 100 here, so I get 2 equals to x over L. Okay. Now, it says that the wire has a final length of 6 meters. After you stretch it, it has a length of 6 meters, meaning that this final length is the original length plus the extension. Okay, so LF, the final length, is equals to original length plus the extension. What is this? From the strain formula, what is this? This is extension. So I put in extension equals to final length minus the original length. I put in the equation. 2 equals to L final length minus original length over original length. Then you find it. 2 equals to 6.0 minus original over original. Okay, just solve this. So 2L equals to 6 minus L, and 3L equals to 6, L equals to 2 meter. Okay, that is my original length. Okay, I write the formula here. Stress is force over area. Strain is extension over original length. Okay, so remember, sometimes the extension is not given. Okay, you have to kind of do a little bit of algebra. Okay, change this one. It can be expressed as this one. Many questions are like algebra type. Okay, some questions are not that straightforward. They want you to derive some equations. Okay, do some algebra like this. Okay. Example 2. A bolt is subjected to a tensile force as shown. The bolt has a circular cross section. What is the ratio of stress at Y to stress at X? Stress at Y and stress at X. We want the ratio, meaning that we want stress Y divided by stress X. Okay, so we do separately. What is stress Y? We know that stress Y is equals to force over area of Y. Because the force are the same here and here, so I can just write F here, okay, instead of Fy. Right. Area. Given here, this is diameter D, and this is 2 times the diameter. So I change this area. I can write it as force over pi r squared. And this is the radius for Y, right? Okay. And then I do diameter equals to 2r. So r equals to diameter over 2. R squared would be d squared over 4. Put it in. Okay, d squared over 4. So we have F over pi d squared over 4 like this. Okay, so simplify this one. This looks complicated. We simplify it. We move it like 4F over pi d squared. That is stress Y. Okay, put it aside first. Stress Y equals to 4F over pi d squared. Okay, let me box this first. Okay, now, how about the other one? For material X, which has twice the diameter, we calculate the stress. Okay, stress X equals to force area X. Force over pi r x squared. So again, we sub d squared over 4, but this is 2D, right? This is 2D. So the d squared, the d is 2D. meaning that I put F over pi and then bracket 2d over 2 square. This, okay? Okay, yeah? So the d I changed to 2d. Now cross, I get F over pi d square. This is stress X. What is the ratio? Divide it. Okay, just divide it. So meaning that from here, I can get stress Y equals to 4 times F over pi d square. And that is 4 times stress in X. Stress Y over stress X equals to 4. This is my answer. Ratio is 4. Okay, so which side experienced bigger stress? The stress at Y is 4 times the stress at X, meaning that over here, material Y will experience bigger stress and material X experience smaller stress, right? Even though the same force is applied, you can see, right? I apply the same force, but one can experience greater stress, another one is smaller stress. Okay. Okay, one more example. Last one. Okay, example number 3. Okay, last one. Data for steel wire on a guitar are listed. The wire snaps and contracts elastically. Assuming the wire obeys Hooke's law, by what percentage does the length of a piece of the wire contract? So we have like a guitar strings, okay, it contracts, right? So it's like compression. It's pulling it inwards. Okay, diameter given, Young's modulus is given, tension is also given. What we want to find here, by what percentage does the length of a piece of the wire contract? Meaning that like what percentage of the original length, right? What percentage of the original length it contracts? That is the strain. Okay, so we use Young modulus, stress over strain. Okay, what we want to find here, we want to find the strain, right? So when we want to find the strain, we need the value for stress and Young modulus. This already given, but for stress, the tension is given, right? So stress is equals to a force over area. You can also find it because the tension is given, the diameter is also given. Okay, so this one we put it like E equals to force over area epsilon. Then we put the numbers 2 times 10 power 11 equals to 20 Newton over area is pi times radius r squared. So meaning that 5 times 10 minus 4 divided by 2 square. Epsilon. Okay, calculate this. And we get just a second. Okay, so epsilon equals to 5.09 times 10 minus 4. Okay, this is the strain. Now remember, strain is the ratio, right? Doesn't have a unit. So strain is this one. And the thing is, this is strain, but they want in percentage. So strain in percentage is equals to the strain 5.09 times 10 minus 4. We just times 100. Okay, so equals to 5.09 times 10 minus 2%. E. That is my answer.